Okay, I should be sharing my screen. So this is the QC1 project from the McMahon lab, and we are using hybrid quantum classical graph generative models to target Alzheimer's disease. My name is Lena.
I'm Nithya.
I'm Akil.
And I'm Mira.
All right, so the problem is that in the drug discovery process, it usually costs like billions of dollars and takes around 5 to 10 years to create usable drugs for patients. But computational methods over time are able to speed up this research, especially with deep generative models like GANs or generative adversarial networks, which can actually generate molecular structures. And so particularly problem is with Alzheimer's disease, which is a progressive neurodegenerative disease, meaning it causes a loss in neuron function, and currently doesn't have many cures and has almost no cures. And it's actually the most common cause of dementia or memory loss. And so our goal is to be able to design a quantum generative model using the GAN to be able to generate potential drug candidates that are effective in curing Alzheimer's disease. All right. And so the main architecture for the GAN, which is the model that we use, is that it consists of mainly two parts. And these are the generator and the discriminator. And so the generator is the thing that actually generates these synthetic molecules or potential drug candidates. And so it takes in SMILE strings from a dataset library called QMN. And the discriminator is the one that actually evaluates whether these generated molecules actually resemble real-life drug compounds and are able to act as a drug. And so continuously over time, this generator will improve by fooling the discriminator until it makes an actual good and effective drug candidate. And so you can see that you can see the amyloid beta here. And so this is thought to be the main cause of Alzheimer's disease. So specifically what happens is that when there's an excess of amyloid beta in the brain, it causes these plaques. And so these kind of inhibit the brain's like functionality and cause like a loss in cognitive ability. And specifically it causes like the entanglement and dysfunction of certain proteins like tau proteins, but there's a lot of them. And so our plan is to be able to generate molecules that can break up or prevent these plaques from even forming in the brain in the first place.
So an important factor that needs to be discussed is the blood-brain barrier. So the blood-brain barrier is a semi-permeable membrane that separates the brain from the rest of the body. When I say semi-permeable, I mean that it's very selective. 100% of large molecules are blocked, and over 98% of small molecules are blocked. To pass, it must have some characteristics, such as lipid-soluble, uncharged or slightly positive, and a small weight. The reason why it is so important for the blood-brain barrier to exist is because it can't let large molecules just pass by, as the brain is so important to the body, so there needs to be some kind of barrier that protects it from unwanted molecules. However, when making a drug for Alzheimer's that is meant to go into the brain where amyloid beta is accumulating, the molecule has to be able to pass this blood-brain barrier, because putting it through the brain is the main method of receiving the drug. So because of that, our project also accounts for passing the blood-brain barrier, as well as making sure that it inhibits amyloid beta. To make sure that our molecule is BBB permeable, we use molecular descriptors. Essentially, these are values that represent the structures within a molecule and its chemical properties. So if the molecule wants to pass through the blood-brain barrier, it must have these certain properties, and using molecular descriptors, we can see whether or not it does have these properties. Specifically, the method we use is called the boiled egg method. And essentially, this is a graph-based method where you can see on the image on the screen, there is a yellow circle, and inside that is a red dot. So this image is taken from an example they used of nicotine for the nicotine molecule passing through the blood-brain barrier. And essentially, the yellow circle, it represents the values that can go through the blood-brain barrier, while the white part is the rest that cannot be going through the blood-brain barrier. And likely what would happen is it would either get absorbed in the pathway there, or just remains in the brain but not passing the blood-brain barrier. So Using this method, we can calculate the values based off of lipophilicity and polarity of the molecule, and then see whether it lies inside the yellow circle, meaning that it would pass, and or whether it would not. Using this, we're able to check if our molecules are actually BBB permeable, which is really important for actually receiving the drug for the patient.
To increase the likelihood of inhibiting amyloid beta, we focused on detecting certain functional groups that are known to enhance molecular performance. Our very first checker is the aromatic ring checker that looks for rings that can strengthen drug binding by stacking with amyloid beta. And we also have our hydroxyl group checker that is aimed at improving solubility, and that is crucial for bioavailability. We also have our amine group checker, which helps identify molecules that are more likely to permeate and cross the blood-brain barrier. And finally, we have the carbonyl group checker that looks for groups that can stabilize the molecule and thus make it more viable as a drug candidate. And in the corner, you can see some examples of amyloid beta inhibitors. And each of these checkers that we've previously mentioned help us prioritize molecules with features that are both functionally and physiologically relevant. But beyond functional groups, we also design checkers for molecular behavior and structure, which are key factors that are effective in the real world and in the brain. One of these checkers is for rotatable bonds, which ensures that the molecule has the flexibility to interact with and attach correctly to amyloid beta. And we also have our self-aggregation prevention checker to help filter out molecules that might clump together and build up, and that would then reduce efficacy. Then we have our small size and flat structure checker to increase the likelihood that the molecule is drug-like and can permeate those tight biological spaces and thus increase validity. And lastly, we have our electrostatic interactions checker that confirms that the molecule has the potential to form stable interactions with those target proteins. And lastly, after applying all of these checkers, we're left with a database of 55 promising molecules. And here's a breakdown of our three-phase approach to discovering novel drug candidates against amyloid beta plaque. Our first phase is for property checkers, and we start by researching the molecular properties associated with the activity against amyloid beta and BBB permeability. And based on this, we developed those checkers that were previously mentioned that screen for those traits. And then those checkers are then run across the QM9 and zinc molecular datasets, and from there we could build two separate databases, and one of those is for molecules that pass the checks, which is our desirable set, and one for those that don't, and that's our undesirable set. Phase 2 is generation, and here we use a hybrid cycle-GAN model with a quantum generator and classical discriminator to generate novel molecules that can basically bridge the undesirable and desirable datasets. And to assess model performance, we can use several criteria like the solubility, synthesizability, drug-likeness, and crucially, the checkers from phase 1. And finally, in our improvement phase, we iterate and we experiment with different model architectures, and we tune weights and modify our set of checkers to see what combination leads to the most promising outputs. And this pipeline makes sure that there's a balance between relevance, feasibility, and optimization.
In terms of our future work, currently we're finishing up and trying to get results from our cycle-GAN-based model and refining it by testing different hyperparameters, architectures, or different combinations of the checkers that Nithya previously mentioned. We're also exploring new machine learning techniques and trying to incorporate them, as well as running this on actual quantum hardware, since we submitted a paper previously in April of 2024, and one of the biggest recommendations that we got was to actually run it on the quantum hardware, but we currently have issues with finding the funding to run it on this. But once we're able to, we're hoping that the efficiency and resource usage are going to improve significantly. There are also additional checkers that we haven't completed yet, but we do want to incorporate into our model, like the ADMET properties, absorption, distribution, metabolism, excretion, and toxicity, that target different things that we want to check for our molecules. For example, for absorption, we want to check if this molecule can be absorbed into the bloodstream, distribution to see if it reaches the right tissues, metabolism, see if it's metabolized in a non-toxic way, excretion, make sure the molecule can be excreted properly, and then toxicity, make sure the molecule isn't toxic. We also want to check into binding energy and look into further checkers that are related to amyloid beta. We want to acknowledge our research advisor, Dr. McMahon, for his guidance throughout this project, ASDRP for giving us the chance to conduct this high-level research and share it, and our previous QNet GAN group members, Adelina Chow, Max Sui, and Linda Cheng. And to the right, you can see the references for our project, the JEI paper, and the IEEE conference proceeding. Thank you so much, and let's open the floor to questions.